an act to follow. Don't expect any skiing or anything like that, or maybe that looked like dancing, I'm not sure. Hey, it's really great to be here and talk to you about Sidewalk Labs and what we're trying to do up in Toronto and how we're trying to really change urban development. I'm going to go through these. You're not going to see a lot of outlines in the future, but I thought I'd have to give you a little bit of a guide. I'm going to talk to you, what is Sidewalk Labs? What are we all about? Why are we doing mass timber? What's sustainability and how do we do that? Fire safety, which is a preoccupation for tall buildings, and how we addressed it in a new way. And then finally show you how we develop a proto-model so that we can invite awesome architects in to use some of these tools to create amazing buildings. So Sidewalk Labs was created by the founders of Google, Sergey and Larry Page, as were mentioned. And they contacted Dan Doctoroff. Dan Doctoroff was the deputy mayor of New York. He was presiding at when the High Line actually was built. And he also was the CEO of Bloomberg. So a very different type of person, right? Somebody who was running a city, running large organizations of a different kind in finance, contacted by these entrepreneurs who started Google. And their idea was, could we do something together where data becomes a foundation of how cities would be designed, so we can take all the advantages of the design of architecture and engineering to make a place. So Sidewalk Labs was born out of that conversation and becomes another one of the bets. So Google is obviously the big company that reports into Alphabet, and these are all the bets, and some of them you may know, some of them you don't see. Things like Nest thermostats are in there. There's other technology that you see as a brand name, but these are the companies. So it's an interesting group of people. So Dan Doctoroff is a city person, right? He knows how to develop a city, so he starts to bring in former public servants. We have people focused on education and health inside of our organization. Then we have urban planners, architects, as you would traditionally have maybe in a development office. And then you have technologists, right? So we have all the data engineers and people who like robots and programming and all that. So in 100 people, we have a very broad range of skills. Really one of the first times I've ever seen a group like that all under one roof, trying to design something together. And boy, we had a hard time thinking of how we talk to each other even, because we all have a different pace. The technologist is like, I'm gonna open up an app in a couple of days, and an urbanist is saying, planning takes a long time, the people have to adapt, they have to take agency over the space. So when we think about what this data question was, there have been some big revolutions. We can discuss which are the exact ones to put up here. But basically, the steam engine started to connect spaces. Definitely, the United States made the cities occur in different spaces and different rhythm. The electric grid totally changed, especially tall buildings, right? A 5-story walk-up was not going to be a 40-story walk-up. It was going to be an elevator. So buildings started to grow and our cities started to get taller. And then automobile highways started to disperse all of those train stops across the land. And so what happens when digital becomes that same piece of infrastructure, that everybody taps into it just like the water that comes to your home and to a building? But then we started to say, what's happening in urban environments today? We have a lot of challenges. There's unaffordable housing, there's longer commutes, all that paving and city and urbanization has these weather events, and we just saw some of the solutions for those. And then you end up with this inequality, and this is a map of Toronto, but it could be a map of anywhere, right? So in the city center, we had the people with lower income. On the outside, back in the 70s, the suburbs were taking all those higher income groups and residents. As time goes on, you can see the outside, that blue side with a higher income, takes over the urban centers, and what happens? People get priced out and get pushed with lower incomes out to the outside of that area. Now, the people who have to service all of these areas and work together have the longest commutes. The people least capable of actually paying for those commutes have the longest commutes and the most expensive. So this is part of the challenge in all of our reurbanization that we see around the world today. This is Toronto, and this is where the project got started. Sidewalk was looking for the right project to go after. This one definitely was the right one. It had the federal government attached to it, it had the provincial government, and it had the city of Toronto. And basically, like a lot of our cities, they had industrial sections of them. They were on the waterfront, but they had a barrier to the rest of the city. Toronto, unfortunately, has an elevated highway and a railway parallel blocking its use of the city. And we interviewed people in Toronto saying, when's the last time you were at the lake? And they actually had to pause and say, oh, I think I was there 5 years ago. Could you imagine Chicago if you asked somebody when's the last time they went to the lakefront and they told you it was 5 or 10 years ago? So they were totally blocked from this experience, and that was part of the rejuvenation of this downtown area. And so this is all the industrial site that this is today. It's basically a brownfield site. So we responded to the RFP. It was in 2017. In 2018, we were awarded in 2017. In 2018, we actually came to an agreement of what that work process would look like. In 2019, we completed a master plan and submitted that. That's been under review. It's under review across the fall right now, and we hope for a final result in Q1. On my plane ride over today, it was announced that we got through our first hurdle actually on this project, and we're moving on to the next phase of negotiations, which is excellent. It's a big thing. We've been working on it for years for today's news, so this is a big event. What comes next, though, lots of negotiation continues to see if we can really make a full project out of it. But we got through the first hurdle, which is through Waterfront Toronto, the agency in charge of our process. Now the federal government, the provincial government, and the city government get into a detailed review of what we've proposed. The goals of the proposal are job creation, housing affordability, sustainability, a whole new system of mobility, of autonomous vehicles, and an urban innovation section of the city where they can foster. Toronto has become a very tech-centric city, and they want to grow that more. And of course, we ended up having to talk about digital privacy because of who we are and because of all this data being used. If it's all interconnected, how is it protected? How does the public stay protected? So if you want to read our master plan, it is online. The overview is 200 pages. The plans and the urban innovations constitute another 1,300 pages. Somewhere inside of the urban innovations, I think it's page 196, you'll see buildings. It's about 300 pages long. And these are all about the innovations that we've put in and how they would work to create a new platform for a city to leverage. One of the most fun things about this project was really engaging with the public. We had 21,000 people with person-to-person interaction, so we held groups like this, and then we broke into tables and working sessions about what people wanted in their city. We had 270 people actually interacting online with us. That's not just downloading a document. And then we have a lab there, and we had about 11,000, I guess it shows here, people come and actually visit us in the lab and do some work, and I'll show you one of those examples. But we tried to invite as many of their opinions in as possible to tell us what are their aspirations for this land. This land, the 600 acres, has been sitting there for 50 years, basically as an industrial zone. Here's a map of the space. And up in the upper left-hand corner, there's a word, you may not be able to see it in the back, but it's Quayside. It's the purple L. That is phase one, really, of the project, and the one that we're talking about directly with them that we were awarded today. And that has about 3.2 million square feet of construction already in the precinct plan for Toronto. We thought that Villiers West, that piece on the island there, had to be incorporated. It's another 3 million square feet. And that's because some of our innovations require more scale. We proposed a thermal loop to heat exchange between all of the buildings. And at 3 million square feet, we couldn't get much efficiency out of it. The factory that we want to build these buildings also needs about 5 or 6 million square feet to pay for the factory. So we made that suggestion. That one got pushed back today, by the way, in the note, and it will still be discussed, I'm sure. The rest of the area, we thought whatever innovations really go well in Quayside should be multiplied across the rest of the area, right? Because the more scale you get in exchanging heat, autonomous vehicles, factory buildings, the better and better we can get at it and show the world where it can go. Because don't forget, phase one is only phase one. There's lots more development after that. Here's a little image of what that could be. It's about 60–75% residential. It's a mixed use. This was diagrammed out, obviously, with timber buildings throughout. So I think this would probably be the largest timber community in the world today. Across the street, it's been awesome. The other developers now have joined, and they are building 2 more timber buildings. That's done by the Heinz Corporation. And George Brown College has their new library called the Arbor, also in that location. So we end up with this, on both sides, not just our development, but in the whole area, an entire timber neighborhood. So a little bit of our approach to design. This is around master planning. We use a generative design tool, and so we say, which one is the best layout? Do you want daylight, affordability, walking, views? We ended up with thousands of variables, not just these. And we started doing iterations on how we could design the city. But not only did we want to show about the design of the city and how we could iterate it, we started modeling what the outcomes would be. So if I start finding spaces inside of the city where it's dark, there's not much wind, and there could be a buildup of humidity, I have a mold area. So we started to talk about how will this impact the operating model of the city if we know where these pockets are. So can we change the way we clean spaces on a day-to-day in certain places that would have this type of environment? And on the sunlit places, we could lower maybe some of the cleaning regimes that we had. So we started to optimize how the city would actually operate the streets. We started feeding the computer systems in with all these different cities, so there were all kinds of variables of layouts that they could think through. And then finally, we gave it back to the residents. We gave them 8 variables at a time. A couple thousand would be hard. And they could dial in, do they want a park? If you get an acre of park, do you want it all split up against each parcel? Or do you want one big park in the middle? And the citizens then starts to have trade-offs. How do I want to experience my city? There's a happy face and an unhappy face. So if they hated their result, they could vote on it, and if they loved their result, they could vote on it. And they got to see all these variables. Do you want one big dense building and lower other buildings, or do you want all the buildings to be about uniform? Do you want a grid pattern, and so on? This was terribly fun, I have to say. And we get the results, and then we would change the variables for the next groups that came in. So why mass timber? So why do we do it? Happens to be that Canada has a lot of it. They have about 10% of the world's timber. And then we started looking, where do we have a lot of buildings, tall buildings going up? And the dark yellow is where labor prices are very high. The light yellow is where labor prices are quite low. So you say, where can I have low labor prices in a factory supplying into a high labor price market that has a lot of buildings going up? And you can see it splits up pretty much on the east and west coast. Texas is also in there, but if you note, their labor cost is quite low. It's quite a light color in here. But this is how we started plotting, where should we put a factory to start building these buildings? Toronto, you can see up in the upper right, is actually in a pretty good spot to find a good labor market importing into a major city. Toronto is the fastest growing city in North America right now, by the way. So then we started looking at the supply chain. So we need to go back to the forest. What kind of timber do we need to be cultivated? These are tree farms. How do we collaborate with the local sawmills so they create the right type of timber? Dimensional lumber isn't what we need. We need a very well dried out timber in order to make the strength panels that for our buildings. And then manufacturing, shipping to the site, and then assembly. So we think all of our timber has to be certified by third parties. We want to collaborate with the sawmills so they make the right pieces that we need and the right species. We don't see anybody doing factories like this, especially in North America. You do find them in the Scandic and Alpine countries, but not in North America. So we started to design this factory. Our intention is to build an $80 million factory in the Toronto region to actually deliver all the buildings that we showed you on the 3.2 million square feet. We've been going with Swiss designers on factories. They have a lot of technology there. We look at how to do it by hand, and then we look at how to do it by robotics. We looked at our shipping, so the architects have to decide how big is the piece that they need to be able to ship, and how can we make that very efficient. So the factory can be a longer distance if we know our shipping is very full. Timber is great for this because the volume of timber and the weight of timber maxes the truck out almost at the same time. Very unlike steel and concrete, right? You see a steel beam go down the street sometimes on a full truck. In timber, you would always have a full truck. So we looked at, just for fun, this is the elevated highway. If we built the building, a 30-story building out of concrete, and we put all those concrete trucks bumper to bumper down the Gardner Expressway, their elevated highway, it would be 14 kilometers long. If we do the 30-story building in timber, it's 2 kilometers long. So we have efficiency, but also we have disruption. We're mitigating, right? For the neighborhood and the road systems, and the wear and tear on the roads for all that trucking. So this is some of the side benefits that we're starting to get as well. So then we went into how do we assemble this building? So we modeled a building. You know, concrete is typically 5-6 days cure, so you turn a floor about every week. So in 12 weeks, I can have a 12-story building. In timber, we can do a 30-story building. That's the speed of the off-site construction, bringing those pieces in. So I'm going to talk to you a little bit about sustainability. I'm going to go through, here's some mass timber with carbon sequestration. You probably know a lot of it. I'll go quickly. And some of these other elements that are important, cradle-to-cradle materials, biophilic design, reducing waste, and finally some hybrid electric systems. So this is my diagram saying sometimes I think we don't build buildings, we're actually building carbon vaults. It's a nice way to think of it. People don't understand it, but if you actually leave those tree farms for those trees to die in 20, 25 years, they're going to re-emit the carbon dioxide that they have absorbed through photosynthesis back to the atmosphere. So if I cut it down and I put it in a building, I am now going to hold that carbon into that material for as many years as that building lives. 75 years maybe, let's pretend. But not only that, I'm designing my building to be disassembled so all those pieces can be used again in another structure. We do that already today, right? Barns, people who have flooring that they take from an old barn. Well, that's the same kind of system. So what if we design that from the start so all those pieces can be reused?
Wild. We can keep them this way whilst carefully extracting wood and other products and valuing them as they are. By managing them well, we can work with their natural resilience to keep them standing. It's a fact that our growing global population will need to use more wood. And that could be a good thing. Wood is an extraordinary renewable resource, and taking it from well-managed sources benefits forests and the planet. But on their own, natural forests can't provide all the wood that we need. So we also have to farm trees, just like we do other crops, and create a new generation of plantations.
It's great that David Attenborough did that for me. If you want to see it, it's on Our Planet, Netflix. It's a movie. It's about 20 minutes long. It goes further into this subject. I gave you just a little snippet here. But this is a big deal of where this is going and what we could do with it. And I'll get to really the depth of that at the end of my presentation. We also went after cradle-to-cradle materials. So when we did it, we went after the materials that we think get reused the most, meaning during renovations they get disposed of and they need to go back to their natural state when we dispose of them. So we looked at doing, obviously, the timber members themselves, but also we came up with a plaster system that I'll show you later that is cradle-to-cradle, that does our fire protection coatings for us. All of our cabinetry, the same, and our flooring we also buy as cradle-to-cradle materials. These are the things that people consume and have to redo every time they renovate and occupy a building. Biophilic design is how these buildings make us feel, But better than that, they actually have a physiological impact on us, right? So people's heart rates drop. You can measure the cortisol in their saliva, it goes down. So these are good for people. People heal faster. There have been experiments where they heal faster in timber buildings, people recuperating from operations, using the same operation in one building versus the other. We can reduce our construction waste, so that's not only the trucks coming in, but all the waste coming off the site. So it's not only the landfill, it's also the trucking of all that material as it leaves. Thousands of dumpsters. And finally, energy, and this has a big impact. I'll get into it in quite a bit here. This is digital electricity. We're able to use this system to send between 2,000 and 3,000 watts over an 18-gauge wire. This is kind of pretty close to a telephone wire. We can then get rid of a breaker panel, we can get rid of the meter, and we can get rid of half the cable. Every wall plug in these buildings will have an IP address, and now I can infinitely control the loads centrally. Me as the tenant, maybe the landlord, whatever situation we're in. So now I'll get into fire safety, and we'll get a little bit back to digital electricity. Everybody's worried about timber buildings burning and what's the impact. So we decided to take a kind of step back and say, but what's really fires and buildings all about? And maybe we should address this not just about timber, but just about buildings. And that's what I'm going to show you some of these pieces here. So we went after the origination of fires. So we aren't going to have natural gas. Toronto has natural gas in the neighborhood. We are not going to have it to meet our greenhouse gas standards. But also we converted everything to electric. The whole building is electric. When we showed this to the firemen, they said, that's not really helping me, because even those electric coils is a source of fire for them, right? So a grease rag on a coil, electric coil, can still produce a fire. So we went to all induction. And when we went to all induction, they said, now you're doing something really important for us. And so they estimate that we could be between 10 and 17% reduction in fire source by getting rid of the heat in a kitchen. So then we said, how about our electric system? This digital electricity, which I showed you before, it ground faults 30 times faster than the fastest ground fault protection we have out there. It is now not rated as an electric system, it's a data system, so it doesn't go into conduit. I can run it on the surface, actually I can run it without an electrician, and it frees me now of having another electric fire source that's about 17% in Toronto. So between the two, I am now taking away maybe 30% of the potential fires, 35% from a city. That's a big change for them, right? The fire department was really interested in this space. Then I need to encapsulate spaces, right? And there's two ways to encapsulate using timber. Either I have the structural piece and I add a layer that ends up getting charred and protects the structural core of a timber, or I actually coat it, and traditionally this has been drywall. We knew we were going to have these coatings, and we said, but we have this beautiful sustainable timber. Let's coat it with something as sustainable. So we found a cradle-to-cradle substance called shikui. It's only 1,000 years old. Only 1,000 years old. It's used in Japan a lot. And so we started changing the chemistry on it and playing with it, and what type of slurries we could create with it, and how we could apply it. And eventually, we started to build our floor cassettes and put the coatings in there. So we put all of our pipes in there, our radiant heating and cooling, and you'll see that in a minute. We put rock wool in there as an insulator for sound and fire, and then we coat it with this plaster system. We took it to a fire test. They did it in the factory. Then we did it in laboratories. We've done about 8 of these. So on the left-hand side, you'll see on the left is the shikui plaster test. On the right is the same one done with drywall. And you can see the flames starting to come through over here. I'm talking about the 2 panels all the way on this left photo. So then when they lift it off, this is a furnace with heat rising. You can see that the shikui panel on the left is still basically the same. The one on the right is charred through the drywall. Both passed the 2-hour test. But when the fire department sees this, they said, I'd like to walk into the building where the ceiling's not falling on my head. And so we went through this, and we are now taking this to actually a slurry operation that in our factory we can pre-coat, fire protect all of our systems. And then finally, active suppression. We're using mist sprinkler systems. This is a 1,000 PSI system. It's out of Finland. It's usually used in marine, but it's 3/8-inch tubing. We can now run that very cleanly inside of our buildings as well. It uses about 1/10 the amount of water. It also covers our lithium-ion batteries, kitchens, so we have one fire suppression system for the entire building. And finally, in evacuation, we could have occupancy detection. Rescue workers could turn this on. They could look at a building and know where to deploy their resources. If people would like, they can reveal something about themselves. They don't have to. It could just say occupied, but maybe I'm disabled, and I'd like someone to know that I'm disabled and come and send the right rescue workers to get me out of my unit, or maybe I have a family with 3 children. You know, we can think about all the reasons that people might want to reveal more about themselves in these situations. We will finally do a demonstration burn, a 3-story demonstration burn, probably in Ottawa, to take a look at this. But I thought it was kind of interesting. I wanted to show you that we didn't look at fire, just how to protect the wood. We said, how do we make a much better building out of this? And how do we take away some of the risks? So now, this is the outcome of that as well. On the left-hand side is a traditional wall with all those cables and sprinkler pipes or whatever you have passing through them. But now with my systems, I don't have sprinkler pipes I need to put inside. I can put my sprinkler pipe on the surface of that wall and hide it through a piece of trim or a reveal or whatever we can do architecturally. And in the base, I have my electric system is running behind the baseboard. So when I'm renovating my space, I don't tear up the walls now. I don't have a waste stream from that. I actually remove an entire panel out of a system. And I can even reuse that wall again and again. So we totally rethought something as simple as the wall. That's kind of our DNA, is to kind of get back to basics and what could we do. So you can see the sprinkler head is there, the electric system is there, the panel is coated with shikui, and on the bottom right, we put something like maybe a retailer would put their own branding panels on top of this. So now I want to go to the proto model. So we are building the foundation in the factory for great architects like we have here today to pick up this thing and do something with it, but knocking out a lot of the guessing game of how to make efficient, well-insulated, energy-efficient buildings in a beautiful and sustainable material. So we went through first the massing, and then we went into a building we call the PMX. It's proto model X. X is cool, so we just used an X, I guess. But really, it was our workhorse. We put all of our innovations into one building. And this is what it looks like. A 35-story building it ended up being with an exoskeleton frame. The core does almost no work for us here. It's all really being done at the exterior. This is common in other architectures, but this was the most efficient way for us to do it. These were all the consultants that worked on it. It is a proto model, but it was a full team and full analysis. Site massing program, we looked at programs of all the different things, ground floor plane, commercial space for offices, different types of residential, all the typical things. And if you look at the efficiencies, we wanted to be as efficient as other buildings in the marketplace. Our offices, our floor plate's 88% efficient in timber. Our residential is a little bit lower, and that's because all of our waste has a vacuum system. So we have 3 chutes that vacuum it out. These are our assemblies to build the building. Here are our units. And these are our floor plates, how we assemble them. So we do digital modeling. Right now, you saw the physical piece before. We're actually doing physical build-outs of these, so we can study them. This is how the floor plates would fit in. They all have interconnections. These are some of the areas of how a resident would control their unit. So on the left-hand side, they have a budget. So instead of getting your electric bill at the end of the month, you determine it at the beginning of the month. And then it regulates your apartment to actually produce that bill at the end. If one day you say, I don't care if I spend more money, I'm too cold, it'll tell you it'll cost you $3 to turn up the heat for the next 10 hours or something like that. We're working with Ori and robotic furniture and IKEA. And finally, we have remote storage for our belongings, so we could reduce the size of the units and use the basement levels. and they can all be recalled by small robots. This is kind of some of the layouts we had, some of the space planning. We have not gone through interior design. These were all really trying to get test fits in front of everybody. You can see we constantly talk about how these spaces get assembled. You could have amenity spaces in like co-living where people have smaller units. They can have shared spaces. So we looked at cooking and eating, more active, medium activity, laundry and study, quiet space. And this is a factory that we've been working with that models everything that we're designing. They're in Switzerland. The name of the company is Rengli. And these assemblies are telling us how many steps we have to assemble it, how difficult it is to assemble, and which processes could be automated. We are intending to build one of these factories in Toronto. It will be our first one, and we anticipate building more of them around the world. All the pieces are stacked for their order of assembly. So at the end, we say you could still do things with these buildings. I'm almost embarrassed to show these images after what we have just seen, but the concept is that we produce something from a factory that can be customized. This is a little bit of what a streetscape could be in this timber community. So the question is, could we solve something bigger for the future? And so I just want to tease our minds a little bit about thinking about that future state of 50 years. Could we do something bigger than building a timber community? And so could we house the world? Could we use this process and start capturing more CO2? And so we took a quick calculation and we said, if the annual population growth is 1.1%, it's 83 million people. If people that need new houses because their buildings expire every 50 or 75 years would need another 154 million people would be housed into new housing every year. And then if we could house all the homeless people on Earth, 120 million over 10 years, that would be another 12 million people. So we need to house 249 million people every year on Earth to reach this goal. And what if we did it all in timber? Is there enough timber supply in the world to do this? When we presented this to the Nature Conservancy and the World Wildlife Federation, they believe that we can reduce global gases, CO2 emissions, by about 11% by taking a step like this. So I will skip the rest of this. And I just want to say, for us, this is really just the end of our beginning. We've laid the platform for a really bright future of mass timber construction across the globe. Thank you.